Welcome. In this chapter, we will cover the chemistry of alkynes. An alkyne is a molecule that possesses a carbon-carbon triple bond. The carbon-carbon triple bond is composed of two pi bonds, utilizing p orbitals between the two carbons, and one sigma bond, which uses an sp orbital between the two carbons. Each carbon also contains one sigma bond with another atom, which is using an sp orbital. Since an alkyne has two pi bonds, they have a lot of the same or similar reactivity to alkenes. The electron density of this pi bond is able to act as a nucleophile. Acetylene is the simplest alkyne. It has a carbon-carbon triple bond with two hydrogens on either side. Triple bonds are prevalent in many different natural products. We are able to name alkynes in a similar fashion to how we label alkanes. We begin by identifying the parent chain, but in this case the carbon-carbon triple bond should reside within the parent chain. Afterwards, we identify and name the substituents, and then we assign a location and prefix to each of the substituents. If possible, we would like to give the carbon-carbon triple bond the lowest number. The carbon-carbon triple bond location is placed either just before the parent name or just before the -ine suffix. Let's take a look at an example. First, we begin by identifying the parent chain. In this molecule, the parent chain should have the triple bond within it. For example, we can look at this 1, 2, 3, 4, 5 carbons, and then if we were to go down towards this alkane, we get to 6, 7, 8 carbons. However, that does not include the triple bond. So instead, we must go up towards the triple bond where we get to 6 and 7 carbons. The parent chain of this would be a heptyne. Then we can assign the location of the triple bond. We want to give the triple bond the lowest number possible. In this example, we have 1, 2, 3, 4, 5, 6, 7, and we can put the triple bond either at the 2 position or at the 5 position. In this case, we're going to want to put the triple bond at the 2 position. There are two options for placing the location of the carbon-carbon triple bond. We can replace them before the parent name or before the suffix. Another naming convention for alkynes is to use the common name. The common names are derived from acetylene and refer to the substituents attached to the basic acetylene. For example, if a methyl group is on one side of acetylene, it would be considered methylacetylene. If we have multiple substituents on either side of the acetylene, we can name each of these substituents. For example, diisopropyl acetylene or phenylpropyl acetylene. Depending on how many substituents are attached to the alkyne, we can have either a terminal or an internal alkyne. A terminal alkyne will always have a proton attached to one side, where an internal alkyne will have two carbons attached to either side. In general, hydrocarbons are not very acidic. However, terminal alkynes are much more acidic than alkenes or alkanes. The pKa of acetylene is 25, which is 19 pKa units more acidic than ethylene. This means that acetylene can be deprotonated by a strong base to form the acetylide ion. This ion is going to be more stable than if we had a negative charge on an sp2 or sp2 carbon. The lone pair is more stable because it occupies an sp orbital. The sp orbital has 50% s characteristic as compared to 66 or 75% p characteristic on an sp3 or sp2 orbital. In order to deprotonate acetylene, a base's conjugate acid must have a pKa greater than 25. This means we generally are using a strong base to deprotonate acetylene. Any terminal alkyne can be deprotonated by a suitable base, and this will produce an alkynide ion. This is the second example of a carbon with a negative charge that we've generated so far in this class. This means that we have access to nucleophilic carbon. We can compare the pKa table to look at bases that will be strong enough to deprotonate acetylene. Any base that has an acid with a pKa higher than 25 will be suitable. Now we'll begin to look over some of the reactions that can be used to prepare alkynes, as well as some of the reactions that alkynes can undergo. We're going to see a trend within these reactions, that a lot of the reactions are similar to reactions that can occur to alkenes. For example, we can prepare an alkyne by the elimination reaction of a dihalide. In section 8.7, we looked at how an elimination of an alkyl halide can produce an alkene. The preparation of an alkyne is very similar, but this elimination reaction will need to occur twice. Each elimination produces one pi bond. These eliminations will occur using the E2 mechanism. We start by deprotonating the beta hydrogen. These electrons then form the pi bond and the leaving group leaves. After this occurs once, it can occur twice. We can then deprotonate another beta hydrogen and have the leaving group leave to liberate the alkyne. We can do this reaction on both geminal and vicinal dihalides. Geminal refers to the halogens being attached to the same carbon. Vicinal refers to the halogens being attached to adjacent carbons. In order for this reaction to occur, we're going to use excess equivalents of NaNH2. This will shift the elimination towards the equilibrium of the products. Since the product is an alkyne, the third equivalent of NaNH2 will deprotonate the alkyne. We then will need to use an aqueous workup so that we can reprotonate the alkyne at the end of the reaction. Overall, we can prepare a terminal alkyne by treating a dihalide with excess sodium amide followed by water.